In this video, we're going to revisit the concept of the inverse of a function and apply this specifically to quadratics. We're also going to explore the idea of restricting the domain of a quadratic function in order to make its inverse a function as well. First, let's just remind ourselves that taking the inverse of a function means swapping inputs and outputs, or swapping x and y values. For example, if the point 1, 2 is on a function, then when we take the inverse, 1 and 2 are still going to be associated with each other, but instead of 1 being the input and 2 being the output, it'll be the other way around. 2 will be the input and 1 will be the output. In other words, we swap x and y. That means we're going to be graphically reflecting the original graph in the line y is equal to x to get its inverse. As an example, if we take the parent function y is equal to x squared, a parabola opening upwards with its vertex at the origin, then taking the inverse of that, swapping all the x and y values, is going to reflect it in the line y is equal to x, the red dotted line here, and is going to give us a graph that looks a bit like that. That's a sideways parabola. So the inverse of y is equal to x squared is this sideways parabola, and that's not a function. Remember that a function is something that has only one output for any one input, only one y value for any one x value. Graphically, it means that a function passes the vertical line test, and we can see that this green graph fails the vertical line test. A vertical line will touch the graph in two places. So the inverse of a regular parabola, y is equal to x squared, without any restrictions on it, is not a function. If we want to look at that algebraically, if we start from y is equal to x squared and we swap x and y, we get x is equal to y squared. Then, taking the square root of both sides, we get the positive and negative square root of x is equal to y, or y is equal to plus or minus root x. We can see that for any x value we plug in, we're going to get both the positive and the negative square root. That's going to be two different outputs from one input. That's not a function. If you're having trouble remembering why we need to put the plus or minus over here, take a look at this as an example. If we were to go back one step to here and put in 4 for x, we would get 4 is equal to y squared. This means find all the values that would go here that when squared give you 4. And we know that there are two answers because 4 is equal to 2 squared, or 4 is also equal to negative 2 squared. Therefore, to preserve both of those answers, when we move to this step, we have to put the plus or minus, because if we didn't, we would only be asking for the positive one, and we would lose this one. As a general rule then, remember when you introduce the square root sign when you're solving a quadratic, you should be putting plus or minus in front. So we see then that the inverse of y is equal to x squared is y is equal to plus or minus the square root of x, and the inverse is not itself a function, even though the original graph was a function. Let's say you wanted to make sure that the inverse was a function, however. You would need to change the original quadratic in order to make that happen, and the way you do that is by restricting the domain. If we go back to y is equal to x squared, we just saw that when we take the inverse of this graph, when we reflect it in the line y is equal to x, we get something that's not a function. That's because this graph fails the horizontal line test. A horizontal line test going through the function anywhere except for the vertex is going to pass through twice. Therefore, its inverse is going to fail the vertical line test. A vertical line going through here anywhere except the vertex is going to go through twice. We can change that, though, by changing the original function. If we go back to y is equal to x squared and chop off the left-hand side, what that's going to do on the inverse is it's going to get rid of this bottom side. You can see that the right-hand side of the original parabola is reflected here in the top half of the inverse parabola. To do that algebraically, what we're going to do is take the original function and restrict the domain such that the x values that we want to keep are only those greater than 0. Those are the ones I've left intact here. We could equally well have restricted it to less than or equal to 0, which we'll do in another example in a moment. But you can see that the most of the original parabola that you can keep is half, because as soon as I start letting some of this part of the parabola stay, then I'm going to have an original parabola that fails the horizontal line test. Therefore, the inverse will not be a function. It'll fail the vertical line test. To go back to what this looks like algebraically, we do the same thing as we did before. We swap x and y. So x is equal to y squared. I take the positive and negative square root of x, and I get this. However, given the restriction in the original question that the domain is restricted to x is greater than or equal to 0, I've only got this part. I can see from my graph that I'm only going to keep the top half of this parabola. That means that I'm going to keep the positive half, only, and I get y is equal to the square root of x. So the inverse of y is equal to x squared, where x is greater than or equal to 0, is just y is equal to the positive square root of x, not both the positive and the negative square root. And by restricting the domain of the original function, we've come up with an inverse that's a function as well. I could equally well have chosen to keep the left side and get rid of the right side of the original parabola. That would mean that I was starting from this, y is equal to x squared, where x is less than or equal to 0, and then I just follow the same process. If I swap x and y, I get x is equal to y squared, take the positive and negative square root of both sides, I get this, but now given the restriction, I'm going to only keep the negative half, because I've started from the left side of the parabola, and to get the reflection in the line y is equal to x, I have to keep the bottom half. So I get y is equal to the negative square root of x. As a general rule, when you keep the right-hand side of the original parabola, you get the top half of the inverse, and when you keep the left side, you get the bottom half. Another a bit more complicated example then, we're asked to find the inverse of f of x is equal to x minus 2 all squared minus 3, given this initial restriction on the domain. If we quickly think about what this function is going to look like, it's going to be a parabola with vertex 2, negative 3, opening upwards. And so then we can see that if we've restricted the domain on the original to x is less than or equal to 2, then we're throwing out the right-hand side of the parabola, keeping the left-hand side. That means when we reflect in the line y is equal to x, we're going to be wanting to keep the bottom half of that sideways parabola. Also, notice that if we know that the point 2, negative 3 is on the original parabola, then we also know that the point negative 3, 2 is going to be on the inverse. So if we do this algebraically, then we replace f of x with y, and we get y is equal to x minus 2 all squared minus 3, and then we swap x and y, we get x is equal to y minus 2 squared minus 3. At this point, we've taken the inverse, but we need to re-isolate y. So we add 3 to both sides, and then we're going to take the positive and negative square root of both sides. And now, given the restriction, we're going to want to only keep the negative half, because we've kept the left half here. That means we want to keep the negative half, the bottom half of the inverse parabola, to make it half a parabola. So we're going to get negative square root of x plus 3 is equal to y minus 2, and then we move the 2 over. And you could either write this as 2 minus the square root of x plus 3 is equal to y, or you could write it as negative square root of x plus 3 plus 2. This one is nicer for not putting a negative out in front. This one is nicer because it clearly shows you that it's a square root function that's been vertically reflected, move 3 to the left and 2 up. Since the question started in function notation, I'm going to put the answer in function notation. So I get f inverse of x. I'm going to choose this one is equal to negative the square root of x plus 3 plus 2. Now to graph that, we know that this is a square root function reflected vertically, and that has endpoint negative 3, 2, and we said earlier that that results from swapping x and y on the vertex of the original function. So it's going to look something like this, shown a bit more nicely here. Here's the original function restricted to the left-hand side, and then when I take the inverse, here's the negative square root function. As a general rule then, if you keep the right half of the upright parabola by restricting the domain to x is greater than or equal to h, where h is the x value of the vertex, then keeping the right half of the upright parabola keeps the top half of the sideways parabola. And if you restrict the domain of the original so that x is less than or equal to the x value of the vertex, you're keeping the left half of the upright parabola. That's going to keep the bottom half of the sideways parabola. So that's helpful for figuring out whether to keep the positive square root or the negative square root when you're taking the inverse algebraically. So that's the inverse of a quadratic and restricting the domain so that the inverse is a function.